Hi, I'm Ethan Zane. Today I'll be presenting my work on integrating TPU soft actuators with drones for adaptive item retrieval. The goal was to enhance drones' ability to handle objects in dynamic environments and make them more effective for tasks like package delivery and search and rescue. So traditional drones face challenges when it comes to safely handling objects in unpredictable environments. And these limitations often lead to increased risks and operational costs. I want to overcome this by integrating a soft robotic gripper into the drone, making it more adaptable and cost-effective for precise object manipulation during flight. Looking at my engineering methodology, the process I followed involved three key steps. Design, I started by designing a soft actuator using 3D modeling software. Two, printing, I used TPU and PLA filaments to 3D print the gripper and drone parts, which allowed for fast prototyping and iteration. This step, I guess, also involves the assembly of the drone, um, and like the motors and also the electronics. And the third step was testing. I then attached the actuator to the drone and tested it under controlled conditions to assess its performance in grasping and stability during flight. The materials I used, I'll just go over some key highlights. The TPU and PLA filaments for 3D printing the gripper and parts of the drone. The SpeedyB flight controller, all in one stack with its speed controller, electronic speed controller as well. The four brushless DC motors, um, as well as, I guess, the LiPo battery, the radio, and the servos for the drone operation. These materials and components allowed me to quickly prototype and integrate the system, which also makes it, when making it both cost effective and scalable. Here are just some videos to showcase the 3D printing process. This one is for the base plate of the drone, which was made of POA. The arms were actually not 3D printed, which I forgot to mention, but that's just due to the, I guess, the breakability of drone arms. And I didn't want to risk the drone just falling apart due to its POA printed arms. The POA was able to be used for the base plate, as well as the top plate for the drone, just because that part is less integral to the flight. This part, this video showcases just a benchy, which is like a benchmark for 3D printers. And this was made out of TPU because I just wanted to see how flexible the TPU was and well, also how good the build quality is. I guess the print quality, right? And all of these parts were printed on the Bamboo Lab X1C. Oh, it's kind of laggy right now, but yeah. The print quality was pretty good. You can see some stringing, but that's ultimately due to the nature of TPU and how it kind of comes out as a glue, because it's like a flexible filament, so it's not as easy to work with than like PLA. This next slide kind of illustrates the step cycle for modeling these soft actuators. So going through the steps, we pretty much design in 3D modeling software. Um, Ultimately, I do want to use FEA and FEM simulations to test these actuators. And then the last step is to, yeah, of course, 3D print the soft actuator. This prototyping phase that we're looking at here is the two prototypes I developed for this project. The left side is the stiff actuator, I call it. It's just more stiff and it has a larger surface area, which allows it to grasp, but with its stiff nature, it has some issues, I guess. It takes more power to bend open, and it won't flex as far as the one on the right, which is like the flexible actuator. And that, and then this one obviously can bend farther, but has less surface area, which is, yeah, it's just two ideas that I prototyped. So finally, looking at the results, the integration of the soft actuators with the drone was successful. And some key results involved the grasping success. The stiff gripper had a 90% success rate of grasping the objects, while the flexible gripper achieved 70%. Looking at flight data, I ensured the flight time always remained under 2 minutes to prevent overheating of the drone components. And yeah, you can see that 10 flights were conducted for each gripper. And oh wait, sorry. Oh, there's a typo, but a total of 12 trials were conducted for each gripper, which you can see here. I accidentally wrote 10 on the one on the bottom, but um, you can see the bending times and its target bending times. Um, and looking at the discussion, some key features I want to highlight include the cost effectiveness of the use of 3D printing, which allows for fast and affordable prototyping. Looking at adaptability, the design is scalable and can be applied to drones of various sizes due to its 3D modeling. And flexible handling, the TPU material allows drones to handle delicate items without causing damage, which kind of goes into biocompatibility. I guess it's easier to work with soft robots than hard robots. And I can see that this will be a direction that the robotics industry would transition to, right? And looking at my future work, my next step will probably focus on autonomous operation. So I plan to integrate AI algorithms to enable the drones to autonomously grasp and retrieve objects. This will involve probably TensorFlow for object detection, and using a model that can be run on um, like a Raspberry Pi or maybe like like a NVIDIA Jetson Nano, right? Um, but yeah, the NVIDIA Jetson Nano is a little expensive for me. But yeah, looking at these future steps, that's what I'll be planning to do. These are some selected references that I used to make this project. And I'd like to finally thank you guys and thank Purdue for allowing me to present my work. And feel free to reach out if you have any questions. Thank you.